concept for anyone looking at Earth sciences. The forces that shape our planet's surface, kind of understanding the very ground we stand on.
Exactly, yeah. We'll be exploring how both the power from, well, deep inside the Earth and the forces acting on the surface constantly mold our landscapes and create the soils we depend on, of course.
Right. So in this session, we're going to cover some really fundamental areas. We'll start by looking at the difference between the Earth's internal forces and its external ones. Then we'll dig into weathering, how rocks break down chemically, physically, biologically.
Yep, all three.
After that, we'll look at mass movements, those sometimes dramatic downhill slides of material.
Landslides and things like that.
Exactly. And we'll explore erosion and deposition, how stuff gets moved around and then, well, dropped somewhere else. And finally, we'll try to unravel the basics of soil formation. Sound good?
Sounds great.
Okay, let's kick things off with maybe a basic question. Why isn't the Earth's surface just perfectly smooth? Like a billiard ball?
Yeah, good question. It's definitely not smooth. And that unevenness is basically the result of a constant battle, a tug of war between two main types of forces.
Okay.
First, you've got endogenic forces. These ones start deep inside the Earth. They're powered by its internal heat engine. Think radioactivity, that sort of thing.
So internal heat is the driver.
Right. And these are primarily the land-building forces.
Okay, so what kind of processes are we talking about here?
Well, the main ones are diastrophism and volcanism.
Diastrophism.
Diastrophism is essentially any process that bends, folds, or breaks the Earth's crust. This includes orogeny.
Orogeny.
Yeah, that's intense mountain building. Usually happens in long, narrow belts. Think of the Himalayas or the Andes.
Got it.
Then there's eperogeny. That's more like broad, gentle uplift or sinking of huge chunks of continents. Less dramatic, maybe, but still significant.
Okay, so big warps and lifts.
Exactly. And things like earthquakes and, the big one, plate tectonics, that constant movement of crustal plates, they're all part of this diastrophism picture, too.
Right, so the internal engine pushes things up, folds them, creates the initial mountains and continents. What about the forces working from the outside them?
Yes. Those are the exogenic forces. They operate on the surface, and they're mainly driven by energy from the sun and, of course, gravity.
Solar energy and gravity, and these are the opposite.
Pretty much. They're the wearing down forces. This includes things like weathering, breaking rocks down, mass movements, material sliding downhill, erosion picking up and carrying material away, and deposition dropping that material somewhere else.
So weathering, mass movement, erosion, deposition.
Exactly. And together, all these external processes work towards something called gradation.
Gradation.
Yeah, basically leveling the land surface. They erode the high spots and fill in the low spots, trying to smooth things out, you could say.
So it really is like this constant battle building up versus wearing down. And the landscapes we see, the hills and valleys, are just a kind of snapshot of this ongoing fight.
Precisely. That's a great way to put it. As long as both sets of forces are active, and they are, we'll keep seeing these variations in relief. Endogenic forces keep creating the differences, stopping the exogenic forces from ever making the planet perfectly flat.
That makes a lot of sense. Now, you mentioned slopes. Tectonic factors create gradients. How exactly does that lead to the slopes that are so important for all these external processes you mentioned?
Well, think about it. When mountains get pushed up, or a whole block of land gets tilted by tectonic forces, that immediately creates an incline, a slope. It creates that difference in elevation over a distance. And once you have that slope, gravity has something to work with. It starts pulling things downwards. That sets the whole stage for water to run downhill, for rocks to weather and potentially slide. It enables all those exogenic processes.
Okay, so the internal forces basically provide the tilted stage, the initial canvas, and then the external forces come in and start sculpting it.
Exactly.
Right. So how do these external forces actually change the landscape? That brings us to geomorphic processes and agents, I think.
Yes. So geomorphic processes are the actual physical stresses and chemical actions that change the shape of the Earth's surface. Gravity. Absolutely fundamental. It's the force pulling everything downslope. Without gravity, water wouldn't flow downhill, landslides wouldn't happen.
Right.
Wind might still blow sediment, but the really significant transport relies on that gravitational pull. It activates the movement, allows the agents to do their work.
So gravity is like the silent conductor of this whole surface orchestra.
I like that, yes.
And these movements always happen because of gradients, right? Differences in height or pressure.
Exactly. Things naturally move from high to low. High elevation to low elevation. High pressure to low pressure. That applies to magma moving inside the Earth just as much as it does to water flowing on the surface.
Okay, this is making sense. We've got the forces, the agents, the role of gravity. Let's zoom in now on how the rocks themselves actually start to break down. That's weathering, right?
It's weathering. It's the breakdown of rocks.
Mm-hmm.
Breaking them into smaller pieces mechanically or decomposing them chemically, and it's caused by exposure to weather and climate, hence the name.
Okay, and the key thing here is it happens in place.
Absolutely crucial point. Weathering happens in situ. That means there's very little or no movement of the actual rock material away from the site during the weathering process itself.
So if a rock cracks open because water froze inside it, that's weathering. But if those cracked pieces then tumble down the hill,
that's mass movement, or maybe erosion later if water picks them up.
Exactly. The slight expansion or contraction within the rock as it weathers isn't the same as transportation. Weathering weakens it, breaks it down right there.
Okay, got it. What determines how much weathering happens and what type? Is it always the same?
Oh, definitely not. Several factors control it. The type of rock itself is huge, its minerals, its structure, any weaknesses like joints or bedding planes.
Makes sense. Harder rocks weather slower?
Generally, yes. Then climate is massive. Temperature, rainfall, how much, how often, freeze-thaw cycles.
Right.
Topography, the slope of the land, affects drainage and exposure, and vegetation, or lack thereof, also plays a role.
So multiple things interacting. Which one is most important? Climate is often considered the dominant factor, especially over large areas. It really dictates the type of weathering that prevails, chemical versus physical, and also influences how deep the weathering goes.
Deeper weathering.
Yeah, the layer of weathered rock, we call it the weathering mantle, or regolith. In hot, humid tropical climates, chemical weathering can be intense and go down tens, even hundreds of feet. Whereas in cold, dry polar regions, it might only be a very thin layer.
That's logical. Warm and wet speeds things up. Okay, let's break down the types. You mentioned chemical, physical, and biological. What's chemical weathering about?
Chemical weathering involves actual chemical reactions that change the rock's composition. They break down the original minerals or dissolve them completely. Water is usually the key player here, along with gases from the air like oxygen and carbon dioxide, and acids from decaying plants.
So like reactions in a chemistry lab, but much slower and outside?
Pretty much. Key processes include solution where minerals just dissolve in water like salt. Carbonation where carbonic acid, formed when CO2 dissolves in water, reacts with minerals like calcite and limestone. Hydration where water molecules chemically attach to minerals, often causing them to expand and weaken, especially important for clays.
Okay.
And then oxidation, think of iron rusting. That's oxygen reacting with iron minerals. And reduction, which is the opposite, happening in waterlogged, oxygen-poor conditions.
So it's not just physical force, but the actual chemistry changing the rock. What about physical weathering then, sometimes called mechanical?
Right. Physical or mechanical weathering is about breaking rocks into smaller pieces, disintegration, without changing their chemical makeup. It's all about applying physical forces.
What kind of forces?
Things like pressure release. When overlying rock is eroded away, the rock underneath expands and can crack. Thermal expansion and contraction from daily or seasonal temperature changes can stress rocks. Frost wedging is a big one in colder climates. Water seeps into cracks, freezes, expands, and wedges the rock apart.
Like a tiny jackhammer.
Exactly. Salt crystal growth in arid or coastal areas can do something similar. Crystals grow in pores and push grains apart. And even biological activity, like tree roots forcing cracks open. Repetition as key cycles of freeze-thaw, wet-dry, heat-cool cause fatigue.
Like bending metal back and forth?
Precisely. These processes can lead to things like exfoliation, where rocks peel off in curved layers, like an onion. You see that creating rounded domes and features called elenodors.
Interesting. And the last one, biological weathering. It sounds like there's overlap, like with the roots.
There is some overlap, yes. Biological weathering specifically focuses on the role of living things. Plant roots physically prying rocks apart is one aspect. Burrowing animals constantly churning soil and exposing fresh rock surfaces is another.
Okay.
But also includes chemical aspects decaying plants. And animals release organic acids that can dissolve minerals. Even humans are biological agents. Things like plowing, construction, deforestation drastically alter weathering rates.
So, from microbes to us, life itself is a weathering force. What's the big picture importance of all this weathering? Why does it matter so much?
Oh, it's fundamental. Hugely important. First, it's the very first step in creating soil. It breaks down bedrock into smaller fragments, the parent material for soil.
Can't have soil without weathered rock.
Exactly. Second, it weakens rock, making it much easier for erosion and mass movements to happen. Imagine trying to erode solid granite versus granite that's already crumbly from weathering.
Big difference.
Huge. Third, the depth and type of weathering mantle directly influence what kind of vegetation can grow, which in turn shapes entire ecosystems and biodiversity.
Right.
And finally, a really interesting one, weathering can actually enrich certain mineral deposits. By dissolving and carrying away the unwanted stuff, they can leave behind higher concentrations of valuable ores, like bauxite for aluminum or certain iron ores.
Wow, okay, so weathering isn't just rocks falling apart. It's foundational for soil, enables erosion, shapes ecosystems, and even concentrates resources.
You got it. It's a critical Earth surface process.
Okay, so now we have all this broken down, weathered material sitting there. What happens next? That brings us to mass movements, right?
Yes, mass movements, sometimes called mass wasting. This is basically the downhill movement of rocks, soil, debris under the direct influence of gravity.
Direct influence of gravity. How's that different from erosion?
Good question. In erosion, you have an active agent on erosion. Water, wind, ice peaking up and carrying the material. In mass movement, gravity is doing the pulling directly on the mass itself. Water or air might be mixed in with the moving material, making it flow easier perhaps, but they aren't the primary transporter like a river carrying sediment.
Okay. Gravity's the main driver, not a flowing medium. Are these always like sudden, dramatic landslides?
Not at all. They range hugely in speed. You can have incredibly slow movement like soil creep, where the ground moves maybe just millimeters or centimeters a year. It's almost imperceptible. Or you can have extremely rapid events like rock falls or debris avalanches, which are very sudden and destructive. And they can involve just a shallow layer of surface material or huge, deep-seated masses of rock and soil.
So, slow creep to rapid fall. Does weathering need to happen first?
Weathering isn't an absolute prerequisite, but it massively helps. It provides the loose, fragmented material, the debris, and it weakens the underlying rock, making the slope much less stable. Most mass movements happen on slopes that are already weathered.
Makes sense. What kind of conditions make a slope more likely to, well, fail?
Several things increase the risk. Weak materials, like unconsolidated sediments or shale. Rocks that are thinly bedded or have joints dipping in the same direction as the slope.
Creates a sliding surface.
Exactly. Fault zones are also weak points. Steeper slopes are obviously more prone. Lots of rainfall that saturates the ground increases weight and pore pressure, reducing friction, and a lack of vegetation. Those roots really help hold soil together.
So those are the underlying conditions. What actually triggers one, sets it off?
The triggers. Often it's something specific. Removing support from the bottom of the slope. Maybe a river undercuts the bank.
Right.
Or humans that excavate for a road.
Right.
Increasing the slope angle or height. Adding weight to the top. Heavy rain, snow accumulation, dumping waste, building structures.
Overloading it.
Yes. Sometimes removing weight from the bottom of the slope can paradoxically trigger failure further up. Earthquakes are a major trigger, obviously. Explosions, too. Heavy rainfall causing rapid saturation. Even rapid drawdown of water levels in a reservoir next to a slope can destabilize it. And deforestation is a big one.
Wow, lots of potential triggers. So it's often a combination of the conditions being right and then some event pushing it over the edge.
That's usually how it works. The slope becomes progressively less stable, closer to failure, and then a trigger event provides the final push.
What are the main types of these movements? You mentioned creep and falls.
Yeah, we tend to classify them by the type of material: rock, debris, earth, mud, and the way it moves. So you have falls material detaching and falling freely through the air, rock fall, debris fall. Slides, where material moves downslope as a more or less coherent mass along a distinct surface. This includes slumps, which have a characteristic backward rotation as they slide on a curved surface.
Like a stoop taken out of the hillside.
Kinda, yeah. And debris slides, or rock slides, which move faster, often along planar surfaces like bedding planes or joints, without that rotation.
Faster, okay.
Then you have flows, where the material behaves more like a fluid because it's mixed with water or air. Mud flows, debris flows, earth flows. These can range from slow to very fast. And creep, which we mentioned, is that very slow, gradual downhill movement.
We hear the term landslide a lot, especially in news reports. Is that a specific type?
Landslide is more of a general catch-all term. It usually refers to any fairly rapid downslope movement of rock, debris, or earth. So it could encompass slumps, debris slides, rock slides, even some faster flows. It's just a common way to refer to these often hazardous events.
Gotcha. And some places seem much more prone to them. You mentioned the Himalayas earlier.
Absolutely. The Himalayas are a classic example. They're tectonically very active, constantly being uplifted, which creates steep, unstable slopes.
Right.
The rocks are often relatively weak sedimentary types, heavily fractured, And they get intense monsoon rainfall.
Mm.
That combination makes them extremely prone to frequent, often large landslides.
And compared to somewhere else, like in South India?
Well, you look at the Western Ghats or the Nilgiris, they're geologically much older and more stable, mostly harder metamorphic rocks, tectonically less active.
So fewer landslides.
Generally fewer, yes, but they still happen. They have very steep slopes in places, often with a thick layer of weathered material from intense chemical weathering due to the rainfall. So you get rock falls from steep cliffs and sometimes debris flows or avalanches, especially during heavy rains. Human activity, like cutting slopes for roads or deforestation, is also a major factor increasing risk in both regions, of course.
Fascinating how the specific geology and climate dictate the style and frequency. Okay, so we've broken rock down, weathering, and we've seen how gravity can pull masses downhill, mass movement. What about erosion and deposition?
Right. Erosion is the next step in moving that weathered material. It's the process of actually acquiring, picking up, and transporting rock debris.
By those agents we talked about.
Exactly. By running water, glaciers, wind, waves, even groundwater to some extent. These agents pick up the fragments loosened by weathering, or sometimes they detach particles themselves and carry them away.
And the carried material can cause more erosion.
Yes, absolutely. That's abrasion. The particles being carried act like sandpaper, grinding against the channel bed or valley walls, wearing them down further. Erosion is fundamentally a process of degradation, wearing down the landscape, lowering elevations.
So weathering loosens, mass movement is gravity's direct pull, and erosion is the active pickup and transport by an agent. Does erosion need weathering first?
Need. Not strictly. A powerful flood or a glacier can pluck solid rock. But weathering makes the job infinitely easier. It provides the loose material that's easily picked up. So weathering, mass wasting, erosion, they're all working together as degradational processes, lowering the land. Erosion, driven by the kinetic energy of the agent, is key to the continuous reshaping.
You mentioned some agents are climate-driven, wind, water, ice. What about waves and groundwater again? How are they different?
They're less directly tied to the broad climate zones in the same way. Wave erosion is obviously confined to coastlines. Its power depends on wind, fetch, coastal shape, not just the overall climate.
Right, location matters most.
And groundwater erosion is most effective where you have soluble rocks like limestone that dissolves the rock chemically, forming caves, sinkholes, what we call karst topography. That depends more on the geology, the lithology, than the surface climate directly, although rainfall is needed to feed the groundwater system.
So the right agent depends on the specific environment and the rock type.
Okay, all this material gets eroded, picked up, transported. What happens then? It has to end up somewhere.
It does. That's deposition. It's essentially the opposite of erosion. It happens when the erosional agent loses energy.
Loses energy. How?
Maybe the slope gets gentler, so the river slows down. Or the wind drops. Or a glacier melts. When the agent doesn't have enough energy to carry its load anymore, it starts to drop it.
Okay.
The heavier, coarser stuff, gravel, sand, usually gets dropped first, closer to where it was picked up. Finer materials like silt and clay can be carried much further before they settle out.
And this fills things in.
Yes. Deposition tends to fill depressions, build up floodplains, create deltas where rivers meet the sea, form beaches and dunes. It's an aggradational process building up the land surface, unlike erosion, which wears it down. The very same agents that erode also deposit.
So it's this whole cycle. Weathering breaks it down, erosion or mass movement shifts it, transport moves it along, and deposition drops it somewhere new, constantly reshaping the surface. That's the essence of it, a continuous cycle driven by internal energy, solar energy, and gravity.
Fantastic. Okay, let's shift gears slightly to something that emerges from all the stuff life depends on. Soil. How does soil actually form? It's not just crushed rock, is it?
Not at all. Soil is so much more complex. It's a dynamic, living medium. There's constant chemical, physical, and biological activity going on within it. It's the result of rock decay, yes, but also the accumulation of organic matter. It's a medium for growth, and it's constantly changing, evolving.
A living medium. I like that. What's the actual process called? Soil formation.
The technical term is pedogenesis. Kedon for soil, genesis for formation.
Pedogenesis. Okay. How does it start?
It really begins with weathering. Weathering provides the raw ingredients, the mineral fragments, the weathered mantle or regolith.
The parent material.
Exactly. Then, very early on, pioneer organisms start to colonize this raw material. Things like bacteria, algae, lichens, mosses. They can survive in pretty harsh conditions.
The first arrivals.
All right. As they live and die, they add the very first bits of organic matter. This starts to form humus, that dark, decomposed organic material.
Okay, humus starts building up.
Then as conditions improve slightly, more complex plants can move in grasses, ferns maybe. Their roots penetrate deeper, helping to break up the material further and adding more organic matter when they die. Seeds get brought in by wind or birds, allowing bushes and eventually trees to establish if the climate allows.
So life builds upon life.
It does. And the roots open up channels. Burrowing animals, worms, insects, rodents start mixing things up, improving aeration, allowing water to penetrate better. Over time, through all these interactions, you gradually develop a mature soil, which is a complex mixture of minerals, organic matter, water, and air, often with distinct layers or horizons.
A gradual transformation from rock fragments to this complex living layer.
Right.
What are the main controls on what kind of soil you end up with?
There are 5 classic soil-forming factors. They all work together, interacting. They are parent material, topography, climate, biological activity, and time.
5 factors. Okay. Parent material, topography, climate, biology, time.
You can think of parent material and topography as more passive factors. They set the initial conditions, the stage. Climate and biological activity are the active factors. They drive the processes. And time is the dimension over which these processes operate.
Passive versus active. Interesting. Let's break those down. Parent material, the starting rock.
Yes, the geological material the soil forms from.
Yeah.
It could be bedrock weathering right there that give you a residual soil. Or it could be material that was transported and deposited by rivers, glaciers, wind that gives you a transported soil.
Okay.
The parent material's composition, its minerals, its chemistry, heavily influences the resulting soil, especially in the early stages. Its texture, like sandy or clayey, and structure also matter. The rate it weathers is key too.
Does the same rock always make the same soil?
Not necessarily. Under different climates or with different vegetation, the same parent rock can lead to quite different soils. And sometimes, different parent rocks under very strong climate influence might end up producing superficially similar soils, especially over long time periods. But parent material often leaves a strong imprint, particularly with distinctive rocks like limestone.
Okay. Second factor, topography, the shape of the land. How does that play a role?
Topography mainly influences drainage and sunlight exposure and erosion rates. Steep slopes tend to have thinner soils because erosion often removes material faster than it can form and water runs off quickly.
Makes sense.
Flatter areas like uplands or valley bottoms tend to develop thicker soils because erosion is slower and water can percolate downwards, allowing more intense weathering and biological activity. Depressions might even become waterlogged, leading to specific soil types with lots of organic matter. The direction a slope faces its aspect also matters for temperature and moisture.
Right, like a sunny slope versus a shady one. Okay, now the active factors. Climate seems huge.
Climate is arguably the most influential factor at broad scale. Temperature and precipitation are the key elements here.
How so?
Well, rainfall provides the water for chemical reactions, for moving dissolved substances through the soil. Too much water can lead to washing nutrients down and out of the upper layers, that's alluviation, and depositing them lower down, alluviation. In really wet tropical areas, you can even get desilication where silica is leached away.
Wow, and too little water.
In dry climates, evaporation dominates. Water gets drawn upwards through capillary action, and when it evaporates at the surface, it can leave behind accumulated salts, sometimes forming hard crusts or hard pans. Temperature controls the rate of chemical reactions and biological activity.
Warmer means faster.
Generally, yes.
Yeah.
Warmer, wetter conditions mean faster decomposition, faster mineral weathering. Freezing temperatures, obviously, slow everything right down or stop it. So climate influences the depth of the soil profile, the types of chemical processes, the amount of organic matter. It leads to distinct climate-related soil zones across the globe.
Okay, climate is a major driver. What about the other active factor, biological activity? Life itself.
Absolutely crucial. Vegetation is the primary source of organic matter, leaf litter, dead roots. This gets decomposed by microorganisms, bacteria, and fungi to form humus. Humus is vital. It improves soil structure, water retention, fertility.
So plants feed the soil.
They do. Plant roots also help break up parent material mechanically and chemically. Soil organisms, from microbes to earthworms, are constantly working. Bacteria fix nitrogen from the air, making it available to plants. Fungi help plants absorb nutrients. Earthworms mix the soil, create burrows for air and water.
The soil ecosystem.
Exactly. The type of vegetation and the intensity of microbial activity vary greatly, often linked to climate. For instance, in cold, wet conditions, decomposition is slow, so organic matter builds up, maybe forming peat. In hot, humid tropics, decomposition is super fast, so despite high productivity, humus levels might be relatively low because it gets recycled quickly.
So life is constantly adding, removing, and mixing things in the soil. And the last factor was time. How does time fit in?
Time is simply the duration that the other factors have been operating on the parent material. Soil formation is slow. It takes time for weathering to occur, for organic matter to accumulate, for distinct layers or horizons to develop within the soil profile.
So older soils are more developed?
Generally, yes. A young soil, perhaps on a recent river deposit or a volcanic ash layer, might just be a thin layer of altered parent material with some organic matter mixed in. It might not show clear horizons. An old soil, one that's been developing undisturbed for thousands or tens of thousands of years in a stable landscape, will usually have a much clearer, deeper profile with well-defined horizons reflecting different processes like leaching and accumulation.
Is there a set time for a soil to become mature?
Not really a fixed number. It depends entirely on the intensity of the other factors. In a warm, humid climate with lots of biological activity, a recognizable soil profile might develop much faster than in a cold, dry climate on resistant rock. So time allows the other factors to express themselves.
So putting it all together, soil is this incredible product of the rock it started from, the landform it sits on, the climate overhead, the life within it, and the sheer amount of time it's had to cook.
That's a perfect summary. It's a complex interplay, and understanding these 5 factors helps explain the amazing diversity of soils we find across the planet and why they're so essential for everything from agriculture to entire ecosystems.
This has been a really fantastic deep dive. We've covered the fundamental forces, the processes like weathering and erosion, the drama of mass movements, and the slow, vital creation of soil. It really drives home that the ground beneath our feet isn't static at all.
Not in the slightest. It's a dynamic interface, constantly being shaped and reshaped by this ongoing conversation between the Earth's interior and its surface environment.
Yeah. The key takeaway seems to be that constant change, that dynamic balance.
Exactly. The interplay between building up and wearing down, creating the landscapes and the soils that life, including us, depends upon.
And on that note, maybe a final thought for you, the listener, to ponder. Given everything we've talked about and thinking about human impact, how might our activities be speeding up or changing these natural geomorphic processes? And what could the long-term consequences look like?
That's a critical question for our time. We are undeniably becoming a major geomorphic agent ourselves.
Definitely food for thought. Well, thank you so much for guiding us through this complex topic today.
My pleasure. It's fascinating stuff.
It really is. And if you found this exploration insightful, please do subscribe to our YouTube channel, UPSC Mindscape, for more deep dives like this one. Thanks for listening, and we'll catch you next time.